How many of you have heard of artificial intelligence before? How many of you are here tonight because they would like to learn more about natural language processing at DATEV? Hi, my name is Alex. I'm the host of the Erlangen Artificial Intelligence and Machine Learning Meetup. Before we get onto the agenda, I would like to start with a short personal story. Just after entering high school, I almost failed a class because of mathematics and English. Back then, fractions and me were not friends at all. Luckily, a few years later, I had a teacher who saw potential in me. So one day, he just handed me a piece of paper and said, "You should try." When I first read it, I felt completely overwhelmed. It was a question sheet for a mathematics competition, and when I first read it, I didn't even understand most of the questions. But he said, "You should try." So over the coming weeks back then, I managed to understand most of the questions and also to solve most of them. And for me, that started a journey where I proved myself that I'm good enough. The journey led me to a PhD in applied mathematics in Cambridge and a professorship in Paris. But during that time, one question became louder and louder, and the question was, what do I do with the gift that mathematics, the abstract and numbers are very easy for me? And I decided to help others find treasures in their data. During that journey, I also saw many thriving meetups in different cities. And of course, I was wondering why there isn't any AI meetup in Erlangen, the city where I was born. So instead of wondering too much about the question, I started up the Erlangen AI meetup last year with our first meetup in April 2019. Since then, the meetup has grown to over 800 members. And today we have edition 24. It's a great pleasure to have you all here tonight. If there's something I can do to make the meetup better for you, please let me know. And now it's a great pleasure to introduce our two speakers for tonight. So we have Jonas, who is a senior data scientist at DATEV, working in the customer-centric design department. He uses machine learning methods to extract customer needs out of a vast amount of text and user behavior data. And together with Thomas Stadelmann, he's working on automatically generating insights from customer feedback. In addition, he's laying the foundation for a customer experience platform. Before joining DATEV, Jonas was a research and teaching assistant in the Department of Statistics and Econometrics. He holds a master's degree in economics and a PhD in statistics from the University of Erlangen-Nuremberg. So welcome, Jonas.
Thank you very much,
Alex. Our second speaker, Thomas. He's a senior data scientist at DATEV also, where he's working on information retrieval, neural search, query log analysis, and A/B testing. Already 10 years ago, Thomas started as a software engineer at DATEV, and over time, his passion for data science is developed. His current research interests include natural language processing, the topic of today, machine learning with focus on deep learning, search evaluation, data structures, and anything commutable. Following his bachelor's degree, Thomas got his master's with distinction from the Otto Friedrich University of Bamberg. He combined his studies with part-time work at DATEV and was awarded the Best Short Paper Award at the BTW 2015 conference. These two data enthusiasts with common interests in natural language processing joined forces back in 2019, and the idea of the DATEV language model was born. So please welcome Thomas and Johannes.
Hi.
Hi.
Hey, guys.
So shall we start with the interview?
Yes.
Love to. Can you describe a little bit more about your backgrounds? Let's start with Thomas.
Okay. Almost 10 years ago, you already told it. I started my path at DATEV with a dual study on information systems. And afterwards, I wanted to continue to get more into information retrieval because I've been working in a department in DATEV, which built a search application, and information retrieval was the most thrilling part of it, I would say. So I wanted to continue in a similar manner, like a dual manner. Unfortunately, this wasn't really possible because there was no official program. So I built one of my own, I think. So I worked part-time, 20 weeks an hour, and did a full-time study at the University of Bamberg with a focus on information retrieval. And afterwards, what always I have a strong interest in information retrieval, and especially the data such search applications generate. And this was basically my path, and this is also my background. And over the years, I made a transition from being a software engineer with a little bit of data science towards being a data scientist with doing a little bit of software engineering.
Thank you. Thank you so much, Jonas. What about you, Jonas?
Yeah, as you already said, Alex, I'm a senior data scientist at DATEV with a PhD in statistics. And I would say within statistics, I cover a broad range from like the absolute classics, like regression models over machine learning and state-of-the-art deep learning. And for quite some time, my research interests was focused on time series analysis, because my PhD thesis dealt with time series analysis in a financial context. And currently at DATEV, I'm working mostly on NLP projects. And as you pointed out, I'm laying the foundation for a customer experience platform. And with that, I'm quite busy.
Okay, cool. Thank you so much. So let's stay with you, Jonas. You're originally not from Franconia, right? So what motivated you to move from the Saarland to Franconia?
Yeah, to be honest, back in the days, my girlfriend wanted to work for GfK. She has a background in the marketing research, and I just wanted to attend an economics master. And so we both decided to move together to Nuremberg, and I never regret this decision.
Great, and you don't regret that. Thanks so much. And Thomas, for you always told us a little bit about your self-designed dual study program. And can you tell us a little bit more about that?
Yes, of course. As I already told you that I really wanted to go more into information retrieval. And this was kind of the reason I chose Bamberg, because I had the plan to actually attend 2 lectures fully dedicated to information retrieval. However, the second the second lecture, didn't take place because the lack of attendees. And what the guys there did was that they created a project. And this project happened to be the foundation for writing a paper. And I'm proud to say that that the result of this paper was the Best Short Paper Award at the BTW 2015 in Hamburg.
Excellent. Sounds great. And so talking about papers and more academic work, Jonas, could you expand a little bit more what you worked on during your PhD? Jonas?
I think he's muted.
Yeah, thanks, Alex, for unmuting me again. Well, during my PhD, I basically worked on time series models in the financial context. So for example, one of my paper, that was my last one, it was joint work together with my colleagues, Christopher Kraus and Matthias Schnaubelt back in the days. And there we tried to analyze the new arising Bitcoin market, like really from a statistical perspective. And with the work, we empirically analyze whether the commonly observed empirical properties from more established limit order exchange markets can be transferred to the new cryptocurrency domain, because now it started to getting regularized, but when we started our analysis, it was like completely unregularized, which is like really cool, like a green field for analysis in contrast to more mature markets. And we recover many observations from more mature markets, such as the asymmetry between the average ask and the average bid side of the order book, but also a lot of idiosyncrasies. And that was one of the most interesting papers, actually.
Cool. Sounds very interesting.
Thanks.
And Thomas, could you expand a little bit more about what you worked on in that paper that got you the award?
Of course. It was, well, the starting point was a paper from the University of Amsterdam. They had this cool project about their own column store implementation. And they stated that you can use their system for implementing information retrieval algorithms. And you can do this in such an efficient way that you can not only use it for rapid prototyping, but you might also consider to use it for real systems, for real production systems. And we looked into that a bit closer and compared it to commonly available inverted list implementations, which are basically standard in information retrieval, and did a rigorous comparison about their efficiency. Unfortunately, MongoDB wasn't that good in that comparison because we really built a real world setup that should resemble a web search engine or an enterprise search. But what's pretty cool, at DATEV, we ended up using MongoDB in one of our systems for analytics where column stores really are good.
Excellent. Very nice. So now you're both working at DATEV. How was the transition from studies and the more academic side to DATEV? Let's start with Jonas, maybe.
Yeah, it was somewhat stressful, to be honest, because my last day at the university in Nuremberg was the last day of March, and then the first day of April, I had to start at DATEV. But besides that, it was quite good. I have been meeting some of my new colleagues then in some meetings, user experience meetings, and at DATEV we have a mentoring program helping a lot just to get started. So yeah, at the beginning quite stressful, but then it was quite cool to be there.
Excellent. And what about you, Thomas?
Well, what should I say? When I first started at the DATEV, I came straight out of school, so this was kind of interesting. If I can remember, I don't know. But the following transition from doing my master's and working there was just no transition at all, because it was everyday work.
But how has DATEV actually changed over the years?
Quite a bit, definitely. I mean, it's basically the digital age caused a major transition to many companies, but I think DATEV especially, I've seen a lot of things come and go, and but most of the developments I think are very good, and also things like we now do are contributing to this. So to get really into this field of AI, for example, I don't think we had something like this a couple of years ago.
Thank you so much. So now looking back, is there something that you would do different if you had to start again? Who wants to go first?
I can go first.
Yeah.
What I a bit regret is that I didn't do a semester abroad. So I tried it several times, but so between the transitions like from school to my trainingship at the bank, or even then to the transition to university, I always tried it, but I never had the time. So that's what I definitely been regretting. But other than that, no regrets.
Well, for me, yeah, it's kind of a difficult question, because you you always have this hindsight bias, you know. Basically, you could do a lot of stuff differently when you know what the outcome is, right? But to give you an answer to that question, of course, there were kind of decisions that I could have done differently. For example, I also could have done a PhD, for example, after the master's. But I think in the end, it wouldn't be too different where I'm now. So I think I would be pretty closely working with data and this kind of search engine data. So I think there's not too much to regret.
Okay, thank you so much. And is there some advice you would give someone who's just starting out in the EAIML field?
Yes, I think I would start, Thomas, if it's okay. So my advice would be don't panic and don't get frustrated. So take it step by step. I mean, what helped me a lot when I started working with AI was I take some courses on the typical platforms like Udemy, Coursera, and I'm working, because there you can work with hands-on with pre-processed data. So you don't have this real-world messy data where you have to perform data cleaning, cleansing, and whatever, yada, yada. So start with, or at least that helped me, start working with hands-on in the courses, and then dive deeper into theory where it's needed. And especially for NLP, I can really highly recommend reading the blogs of Sebastian Ruder and Jay Alamer. That helped me a lot getting started with NLP. Especially Jay is really a genius when talking about like giving a good intuition for NLP, giving a good intuition for deep learning, and especially he's the king of visualization, and he visualizes perfectly what's going on under the hood. So that's blogs of two guys I can really recommend.
Thank you so much. What about you, Thomas?
Yeah, we're gonna see some of his visualizations, I guess, today.
For sure.
There's not much I can add, but yeah, maybe I think, yeah, basically the same thing. There are so many very good free contents now on the web. So my advice would be just start, and especially if you have a coding background, there are really cool contents like this. What helped me most were the fast AI courses, deep learning for coders. This was really for me a straight path into doing deep learning. On the other hand, I think it's difficult to just do stuff like that in your free time, I would say. I think you always have to apply it always on your job to really stay focused on this, because in the end there's where you learn most of it.
Thank you. So we already touched briefly upon AI and ML. Would you define those two terms for us? Let's start again with Jonas.
Yes. I mean, a hard question. I will try. I mean, at least I can tell you what AI is definitely not. It's my stupid little vacuum bot. So, but okay, let's be honest again. I mean, AI is a fuzzy and really broad word, and often used in marketing context. I think at the last meeting also, Dominic Bayer, my colleague from DATEV, was pointing that out. What's also stressing him a bit, and I can fully agree with him there. What I would consider a real AI, so real AI, quotation marks, is nowadays most often called something like general AI, which is really about systems that are on par or even better than humans on a broad range of tasks. So what we call AI today are systems that are rather very good at a very narrow task, And most of the time we are using machine learning algorithms for that. And I mean, that's not bad at all, don't get me wrong. Perfectly fine as a starting point. Instead, yeah, I mean, it's really exciting to see what's even possible today, and it will be a bright future for AI.
Great. Well, what are your definitions, Thomas?
Yeah, not much to add, but especially if you look at the NLP field, you know, over the time, there didn't really happen too much, especially in the last, I don't know, two decades or something like that. But suddenly with deep learning hitting this domain, all state-of-the-art benchmarks have been cracked. And that's very cool because, you know, natural language has all these properties of fuzziness and implicitness that machines usually don't like at all. And so I think this is kind of a breakthrough. And so deep learning, a subfield of machine learning, is definitely the main driver of today's AI technologies. And there's a good chance that it will still be in the future, I think.
Thank you. Thanks so much for answering all the questions. And now for the last one, my favorite one, what's the impact you would like to have in the world? In this case, I think we can start with Thomas.
Okay. For me as a tech enthusiast, I love working with cutting edge technologies and showing what's possible with it on real world problems. But on the other hand, especially referring to my software engineering background, I want to show you that it pays off to dig deeper into those systems. Because I think in order to really understand what's going on inside this magic, you have to get in touch with the guts. And there's so many amazing contents, as I already said, and Jonas already said, that is completely free in order to get a head start. But in the end, nothing will be more formative than to actually debug into those systems. And that's why I won't let you go here without doing that at the end of the session.
Excellent.
Yeah, for me, I mean, to be honest, I don't now have this heal the world, make it a better place answer. I mean, of course, if I could wish, I would say, okay, let's stop hunger, let's stop war. But I mean, as I grow older, we all know how the world works, and it doesn't work like wishful thinking. So to be honest, I'm happy and satisfied with supporting my friends, supporting my family, try to have a positive impact on my own little world. Yeah, and maybe don't go at cruises anymore, things like that, to get a better green footprint. But besides than that, I think I'm just fine with supporting friends and family.
Well, thank you so much for agreeing to this interview. It was a great pleasure to hand over completely to our two speakers. And before I do that, let me say that they will start out with a more broad overview in NLP. And then towards the end, it will become more technical, should become too technical for some of you. Just let us know and they can adapt. And the mics will be open. So if you have questions, feel free to just unmute yourself and ask them. Otherwise, please feel free to type the question in the chat and I will take care of reading it out. So it's a great pleasure to hand over to Jonas and Thomas for their talk on NLP at DATEV.
Thank you very much. So Thomas is sharing screens and I'm going to start. So thank you very much for having us, Alex. It's a great pleasure to be at the meetup. And today's talk is about natural language processing. So the abbreviation is NLP at DATEV. That's the company we are working on. And so the subtitle is Setting Up a Domain-Specific Language Model. And so without any further ado, let's jump right into the agenda. So today we prepared for you a gentle introduction to NLP. I would start with it. So covering all those basic ideas of a language model. Then we do a smooth transition to the most impactful concepts on NLP, transfer learning. Then Thomas will continue with the key results of our proof of concept. We're sharing some insights there. And then Alex already mentioned it. It's go hard or go home. We do some technical deep dive. We don't want you to go home. So just stay or prepare snacks and drinks for the discussion. Yeah, so let's start with the talk. So let us first define natural language processing for you. I mean, it's like an intersection of many tracks. We have linguistics, we have information and processing, we have computer science, and we have AI, and especially deep learning, and all that blended together is natural language processing, NLP. And we have the definition or we always say that, it's an algorithmic processing and analysis of natural language. That's not like a textbook definition. That's just what we really like to work with. And a little side note, that also works quite well for top management. So we stick to that definition. Thomas, klickst du eins? So I want to start with those very, very big pictures. So in an NLP project, you typically have those like those three themes. So you have the language model, and besides the language model, you have the corpus and the downstream task. And let's start with the language model. So spoken language is evolving over time, and the problem is it cannot be fully defined by formal criteria like a programming language. So we have to come up with a smart solution to somehow capture a spoken language. And there's this data-driven approach, and this is where language models come into play. So the idea now is to take real-world data and learn the language by observing a lot of real-world examples. So many gigabytes of text data. And this is what we call the corpus. So that's the another part, the corpus. And the corpus is basically is just the textual basis for a language model. And it consists of many different data. So we at DATEV, we are a German company. Our clients are mostly German. Our language at DATEV is also German. So in our context, it's about German text data. So we have in our corpus, we have public German text data, for example, Wikipedia. So the aim here is to learn in general the German language, to get syntax, to get semantics. And then our talk is about setting up a domain-specific data. So we have public domain data. We are working in a legal and text domain. So, for example, we in our corpus, we use a German legal. And then we have our DATEV own domain data, which of course is not public. So here, we have also lots of gigabytes of own data we're using there. And then the third ingredients, so to say, for an NLP project are the downstream tasks. So these are the problems you really want to solve with a language model. So for example, problem classification, sentiment analysis, and all the other stuff. We will come to that in a second. All right, let's jump into, or let's dig a bit deeper in the language model. So, or to be more specific, in probabilistic language models. So we have a formal definition for you and also like verbal definition. So the language model basically has two tasks. So the first one is assigning a probability to a whole sentence. And the second one is basically assigning a probability to the likelihood of a given word following a sequence of words. So we try to also give a more formal mathematical definition. So we have a sequence W consisting of words. The length of the sequence is M. So you have word 1 until word M. And then the language model is assigning a probability that we observe the sequence of words. And then the second task, a bit more formal, that's like a conditional probability. So it's the probability of observing word M given the sequence of words W1 until WM minus 1. And the important thing to keep in mind is what is the outcome of such a language model? It's always vector representations. So we always have one vector per word. And the cool thing is that you can perform mathematical operations on it. And here are some vector representations listed. So bag of words, embeddings, and contextualized embeddings. And I will come to that back in a second. So let's immediately jump into transfer learning. And I think all of you, or maybe most of you know this guy. This is Andrew Ng, very famous for his Coursera courses. He is a professor for machine learning in Stanford. And also he's the leading researcher for ML and AI at Baidu Research, which is like the Chinese Google. So it's really like a big guy. And Alexander, I think he's a perfect candidate for the next AI meeting. And he said in 2016, and one on his tutorials, transfer learning will be the next driver of ML success, which is quite impressive when you think of what other concepts are around, for example, like reinforcement learning or unsupervised learning. So this is quite impressive, and I think we should dig a bit deeper into transfer learning. So on the title of the slide, there's also like a definition of transfer learning. Let's jump right into the picture. So the basic idea is you have a source task or a source domain here in this I don't know how the color is called in English, a patrol, maybe something like that. And on this data set, you apply a model of your choice, let's say model A, and then you have another task, or maybe in another domain, it's called a target task. And then also there you apply a model, let's say model B. And now the thing of transfer learning is that you extract as much knowledge as possible from model A and infuse it into model B. And knowledge in this case is like a very general concept. Could be everything from just parameters, some weights, just the vector representations, or a whole model. So that's why we keep it very general on this perspective. And typically, the source task or the data set of the source task is very, very big. And the data available on the target task is rather small or medium size. But why now? I mean, why now transfer learning? Yeah. So why is this a good idea to extract knowledge and infuse it into another model? Well, I mean, there are those really like superhuman performing models. I would say these are the low-hanging fruits where we, as AI researchers all start with. You have all those nice models from Google. You have AlphaGo, and you have lots of labeled data, and everything is perfectly fine. You got a crazy good performance on those models. But on the other hand, there are those domains where labels are rare, labels are because maybe they are costly or they're even prohibitive. And transfer learning is kicking in really at that point. So the idea is now, take your pre-trained model from another domain and just, or let me say it differently. If we would just now apply those hyper good performing models as they are, let's say a classification model, on another target task where they're not trained and they usually perform very poorly. So now transfer learning is kicking in. So we extracting, we reuse models into areas where labels are basically there are less labels. Yeah, as I said before, maybe labels are expensive or even prohibitive. So the idea of transfer learning is you need less labels. You can reuse your models for multiple different problems. You can even solve problems in new domains, and that's what we are observing at the moment. So it's not just the low-hanging fruits. We're digging into new domains. You have faster development because you don't have to always start over and over again from scratch. And of course, it helps us in performance in the sense of scalable AI, scalable machine learning, because if you just have to adapt and not to retrain all the time, you're way faster in those real-world live applications. So far the concept of transfer learning in general, and now let's have a look at transfer learning in NLP. Here from the dissertation of Sebastian Ruder, he developed a taxonomy for transfer learning in NLP, and we are focusing here on sequential transfer learning. So the idea here is you have different tasks. You have labeled data in your target domain, and the tasks are learned sequentially. And why we're focusing on sequential transfer learning? Well, that's what we are doing at our domain-specific language model, and that's what brings us most, or brings NLP most success. There's also, and that's what I marked in red, domain adaptation, because we are always talking about domain adaptation. So this is a false friend at that slide. I love Sebastian Ruder's work, but this domain adaptation, it's a bit misleading. So don't get confused. When we are talking about domain adaptation, it's more like what we're doing technically, but we are located in the taxonomy of Sebastian Ruder. We are located in sequential transfer learning. So let's start with an NLP example of transfer learning, and that's exactly what we are doing in our context. So we start with unlabeled data, unlabeled text corpus, up to 12 gigabytes. And at the end, there's a result, a model, and you can apply every model you like. So what is suitable for your use case, maybe fast text, word-to-wake, BERT. There are tons and tons of models. It's hard to keep up with new models in NLP. And then I give already some examples for unlabeled text data. So it's public German text data like Wikipedia, public domain data like German legal, and our own DATEV domain data. Now, after applying our model, in our case it's BERT, we extract the knowledge. So we extracted the whole pre-trained model. So we keep not just the representations, not just the parameters, but rather both. So the whole model, and infuse our target model with it, so target data. Now the idea is to adapt our model, our extracted representations, to a supervised learning target task, and using our labeled data. Examples for tasks where labels are available is classification, sentiment analysis, named entity recognition, intent recognition, neural search, question answering, text summarization, and this list is very long. These are just the classics, I would say, and we are focusing on classification, sentiment analysis, and neural search. So let's see how transfer learning is also changing research. Here you got a graph of F1 score from the performance of question answering. So it's a squad 2.0. And what you really can see that F1 scores are not that impressive. So one more remark on this point, transfer learning have been very popular and very successful in the vision area. And this is due to the image.net database. It's a public database where there are millions of pictures in it. So in transfer learning, in vision have always been very successful. And what you can see here, so around November 2018, you see this discrete jump. It's also highlighted in red. This is when the first time when transfer learning was really shining in the NLP area, with Wikipedia becoming public and things like that. So you can really see that there's this big jump in F1 score. And it's just really amazing and leading to state-of-the-art results. Yeah, so coming from this evolving of transfer learning into NLP has also a name. It's called the image.net moment of NLP. Okay, now after talking a bit about transfer learning, let's talk a bit more about the results of a language model. So this is the thing we use to transfer the knowledge from unsupervised data or from unsupervised learning to our supervised target task. And the first really breakthrough were embeddings. In 2013, for example, Google released word-to-vec. There are also clothed embeddings. And the idea of embeddings, really general, these are real value dense vector representation, just 1 cross D. For a word. So every word has its own vector representation. And the really cool thing, or the breakthrough thing, is you can perform mathematical operations on it. Here we see an example. So the word bed has a special vector representation. So compared to other methods like the back of words, for example, there you had fully interpretability here, this is a black box. So it's not possible to interpret these vectors, but you get crazy good results, and you can perform mathematical operations on it. So that's really a breakthrough. And those vectors are derived based on Kurokan statistics, which allow to capture semantic similarities. And here on the slides, I have, I would say that the most famous example for embeddings, if you take the embedding for king, subtract the embedding from man, and add the embedding for women, you roughly get the embedding for queen. And here we see some graphical vector representations for it. So that's a really cool thing. But it has some drawbacks, and I will come to that on the next slide. So the vector, the embeddings arising from word to vec or glove, they are not at all context sensitive. So we have an example for you. The bat hits the ball, got exactly the same word embedding than the bat is sleeping in the cave. But of course, two completely different contexts. So on the first sentence is the bat in the context of a baseball game, and in the second sentence is the bat, the animal, the bat, sleeping in the cave. So as you can see on the slide, no context caption at all. It's the exact same vector, and this of course is a drawback of the embeddings. And would be cool to come up with a solution, and the solution is to use models that are built up on the transformer architecture, like BERT, for example, the modeling we are using. And BERT is able to solve this problem and capture the context, and leading us to contextualized embeddings, which is just another evolution of NLP. So as you can see on the slide now, the bat hits the ball and the bat is sleeping in the cave. Bat now got two different embeddings. So here we successfully account for different contexts, and we are focusing on BERT on our natural language model. All right, so far we learned a bit about how a language model works, what are the key ingredients for an NLP project. I talked a bit about transfer learning and the outcomes of a language model, the vectors. And now let's talk a bit about domain knowledge. And little spoiler, but domain knowledge is the absolute key to success if your company is working in like DATEV in a field where there's extremely much domain language involved. So why domain knowledge? So if you, you can download a lot of freely available models. For example, German BERT by DeepSet AI, startup in Berlin. So it doesn't account for any domain knowledge. It's a general model. You can download it. It's quite easy, quite handy. You can apply it and you're done. So that works very well if you are not working, or if your company is not located on a field where much domain data is going on. But the drawback of those freely available language models, they don't contain any domain knowledge at all. So there are now two ways how you could induce domain knowledge or take domain knowledge into account when you're building up your own language model. So benchmark, no domain knowledge at all, German BERT by DeepSet. And then you have two possibilities to account for domain knowledge. The first one, it's called language model adaptation. So you take an existing model, you enrich this model with domain knowledge. In the case of BERT, BERT has 3,000 characters available in its vocabulary, and 10% are always free, not pre-trained, and you kill those. You can fill up those 10%. It's around 3,000 characters with domain knowledge. That's the first thing you can do, and that's what we are mainly done so far. Second thing is you can start from scratch. So you don't use an existing model at all. You build your own model really from scratch. So the proportion of domain knowledge can vary between 0 and 100%. It won't be 0, of course, because domain knowledge is important in your domain, and it won't be 100%, or it won't be 0 because your model have to learn some German to provide good results. And on the other hand, it won't be 100% because just domain knowledge, then the model would understand German, basic German. That's also not successful. So we started with LM adaptation. Currently, we are evaluating training from scratch, but training from scratch is very expensive. So, for example, in our case, I think we could say the numbers. It's around $5,000 per training in Amazon Web Service Cloud, and it takes a lot of time. So it takes 1 week on 4 GPUs. So that's quite something. And with that, I'm done with my introduction and with guiding you a bit to transfer learning. And I would hand over to Thomas.
Thanks a lot, Jonas. Now we're entering section 3, and I'm proud to give you some insights of our proof of concept. First, I want to start with the basic research questions for our language model domain adaptation proof of concept. First question is, does incorporating our domain data improve the results of our domain downstream tasks? The second question, how to set up a domain-specific corpus containing multiple subdomains, might get a lot clearer when we go into the slides and follow our path. And the third question is more about my background from software engineering. I want to know how mature are current open source frameworks for NLP transfer learning, because actually we have to work with them and we have to know, can we really use them even for, say, production systems, right? So first I want to give you an overview for which kind of software and hardware stack we decided, right? On the very bottom, there is a GPU, of course, because if you're doing things like applying a BERT model or training a BERT model, which has millions of parameters, you need some specialized hardware that is very good at parallelized operations, multiplication operations you need for huge matrix multiplications. So on top of this, there is the CUDA framework, that's de facto standard. And on top of this, you basically have the choice between TensorFlow and PyTorch. We chose PyTorch, in which you can implement your deep learning models, because all of the upstream frameworks we chose also had a better integration to PyTorch, or even no integration for TensorFlow. On top of PyTorch is this cool transformers library coming from Hugging Face, where you can find basically all of the architecture implementations that you need to do. Big NLP models. And the cool thing about it is that it doesn't take long from having a new architecture from a paper that recently has been released towards it's implemented in the transformers library. So it's basically made its name for a de facto standard in this kind of stuff. To really get the most benefit out of transfer learning, we chose another framework which is called FARM, and it's coming from DeepSet, which Jonas already mentioned. And this has some nice, comfortable functions. Besides a comfortable training function, you also have this conceptual view completely integrated, that you can stack different heads on top of your language model, so you can really solve different problems with it, like say classification head you can put on top of this, or a named entity recognition head you can put of this. Yeah, it just makes it a lot easier to get most out of transfer learning. What is besides the PyTorch and Transformers libraries NVIDIA Apex. This is a special PyTorch extension that enables automatic mixed precision training. This was needed at the time we were doing our proof of concept. Nowadays, Apex is fully integrated into PyTorch. So if you want to do the same thing, you don't need to worry about this anymore. So what is mixed precision training? Just to give you a hint, it enables you to train faster and to have a smaller memory footprint on your GPU, where resources are very restricted normally. Okay, Jonas already depicted it in one of his slides, that we are using the German BERT model, which has basically been trained on German text already, as a starting point for our domain adaptation.
Can you try to fiddle with the audio output again? So there's a comment from Armin. Do you have your speakers on or not at all, actually, Thomas?
I don't have speakers on, I think, right? I can check this. So now, is it better?
No.
Actually, I can't really hear what's going on outside of my head.
Outside
of my headphone.
It's okay. It seems that there's just a feedback cycle, but
now I
if you cannot do anything about it at the moment, Thomas, then just continue with it.
Okay.
Then please continue, Thomas.
Okay, thank you. So as a starting point, we took the German BERT model. And as Jonas already said, we had 10% of its vocabulary non-allocated, so we could freely choose that for our domain adaptation. So we inserted the top 3,000 most important sentence pieces, which are basically word parts, you can call them, of our corpus. And then we trained the model on, right? In the end, we took about 1.2 gigabytes of raw domain-specific text. And for evaluation, we took two domain-specific classification use cases that didn't have too much labels. Okay, we already know that if you have a lot of labels, this kind of domain adaptation, that doesn't give you a lot of leverage. So we focused on these use cases, and the special thing about it is that each of these classification use cases comes from a different subdomain out of our domain. So one of which is from the service and support domain, and one of which is from the legal and professional domain, which have almost completely different languages, you might say. Of course, they share something, but they are kind of different, right? And we compared our domain adapted model against the original German BERT, so with no domain adaptation, and against a self-trained fast text model. Fast text, because it has a comparable concept of handling word parts, I would say, but it's a shallow model, so not a deep model, and you don't need too much compute. So this would have the advantage of not having too much excessive computation resources that you need really for doing this. What we also saw in our evaluation, that we had a very high variance in the evaluation runs. So we always did at least 25 runs to get a proper statistics and to make a a conclusion which of one is better or not, right? And as we had very little data, we also went for data augmentation. We chose a 4-fold back translation with FAIR6 WMT19 models, which enabled us to get the 16 times out of our data. And here are the results. To answer our initial question, does incorporating our domain data improve the results of our domain downstream tasks? You can see the results in the box plots on the right. For both use cases, we could improve the performance with our domain adaptation. We deliberately omitted the results of the fast text model because they were way worse, about at least 10 percentage points worse than the BERT model. So we are only focusing on the BERT results here.
Do you have some insights on why the fast text results were worse?
We don't really know, but well, in the end, of course, they are. If you're using a shallow net and not really using contextualized word embeddings, I think this should be the main reason why they didn't work that good.
Thank you.
Okay, thank you. The magnitude of improvement for one of the use cases was on par with previous results we read about in literature, which was about 2% points F1 macro improvement. And for the other use case, which had less data, we had a much higher improvement with about almost 10% points in improvement. What's important to say is that this weren't the results of our first attempt. So we had to do multiple attempts. I can tell you a story from our first attempt where we were just sampling documents from our raw corpus as it is. And we ended up with a very imbalanced training corpus regarding our two subdomains. So there was basically a distribution of, I don't know, I think it was worse than 80-20. And this led to the result that one of the use cases didn't work at all. We even got worse results than the baseline. And after having seen this and looked at the data more, we really chose to build a corpus that is 50-50. And having done this, it suddenly worked. And we could produce results like this. From that, we can basically draw the conclusion that especially if you have very different subdomains, there's not one language models to solve all tasks. So it's important to also look into your corpus and to structure your corpus for different tasks which you might want to solve. And another insight here is we already knew the Roberta paper, which focuses on BERT pre-training, and they suggested to completely throw away the next sentence prediction hat. Well, basically, I have to explain, if you're training BERT models, you have, from the initial Google paper, you have two different hats or training functions you can call. One is next sentence prediction, so you're trying to predict is the right sentence following the left sentence, and the other is the masked language model hat, which tries to predict masked words that have been masked in the initial input, and the model should predict which ones they were. And if you leave out the next sentence prediction hat, they figured out that it gets a lot better, and we can confirm this. Without the next sentence prediction hat, we had improvements too. Okay, so this was research question 1. So now I hope it should be clear why we are asking this question, how to set up a domain-specific corpus. Of course, yeah, don't create one big file, keep it modular. We split our corpus by subdomains and even by document types, so we can flexibly choose our corpus for different tasks, right? We might want to solve. And of course, it's important to update or version your corpus because completely new topics may arise, like Corona this year, which a model that have been trained before, say, January or something like this, wouldn't be able to handle, right? Or at least, yeah, wouldn't know anything about it in the initial state. Yeah, the next point, common pre-processing logic using adapters for different data. That should be clear, just for efficiency. And yeah, what we also spent a lot of time in the initial phase was to get sentence splitting right for the next sentence prediction head, which we now know is not that kind of a big deal for a language model domain adaptation. So we in the end we had a very good sentence splitting model, but even with this, the next sentence prediction head didn't improve any of our results. Right? Last question: how mature are current open source frameworks for NLP transfer learning? The good question is all frameworks seem to be pretty stable, but you really have to keep in mind there is a trade-off between rapid progress and stability, and the progress is very, very fast there. So you might expect, you might have to expect that yeah, things might break in future releases. We didn't experience much of that, but yeah, proper environment control, like using Conda and PyPy and stuff. Yeah, this solves the problem, right? To reproduce your results. But the biggest pain are still varying environments, especially if you want to port your environment from, say, a training environment to an inference environment, say from Linux to Windows or something like this. There are still yeah, problems that arise, and it's not that smooth, but it has improved a lot, we have to say. Yeah. The cool stuff about all these open source frameworks is that if it's broken, you can fix it. So just don't hesitate to create a pull request or merge request, and yeah, you can fix it. So now we are leaving section 3, the proof of context section, and now we are trying to get a little bit more fun out of this. So I want to take you on a trip from basic ideas, what is deep learning and what are we even doing here with deep learning, considering its fundamentals, towards looking deeper into the context creating or context incorporating mechanism of the BERT architecture, which is self-attention. And there we are also going to look at some code, how it's implemented. So let's begin. And I'm trying to keep the first initial slides yeah, pretty brief. If there are questions, just yeah, step in. So first of which, why are we doing deep learning? I have a slide, another slide from Andrew Ng. So I can say the name again that Jonas already did. And this slide pretty much yeah, shows what's the strength of deep learning, because about 30 years ago we already had this universal approximation theorem, which basically states that we can approximate almost any function arbitrarily close with neural networks. And yeah, the question is, so why didn't we have this deep learning breakthrough in the 90s? What was missing basically was vast amount of data and the availability of compute power. And that's also what Andrew here depicts on his picture. That's maybe the main difference to older learning algorithms, how he calls it, or classical algorithms. Deep learning techniques scale with data, so you can always get a little bit more, at least up to a specific point from deep learning with more data than with older algorithms. Also, you can obtain good results with comparative ease. If you compare it to all those excessive feature engineering that we are familiar from earlier NLP approaches. I'm just remembering one of the scripts Jonas wrote when he started here, and he was doing some feature engineering for a random forest approach. Yeah, and after we talked, we said, okay, we have to try deep learning. I mean, there is some pre-processing, of course, but the point here is that it's more or less standardized. Okay, you have your tokenizer, and that's doing all the stuff you want. And of course, nevertheless, yeah, most deep learning approaches have produced state-of-the-art results in most machine learning disciplines. So now we are coming to my favorite slide, which might be kind of confusing to some of you, but I just want to show you from my perspective as a visual and coding related person, what for me the main ingredients for neural networks are. Later on, we will go deeper into the architectures and see how BERT actually work. But the main ingredients for me are on the left side, matrix multiplications. It's so important that there's a page that's fully dedicated only to this. You can check it out on matrixmultiplication.xyz if you don't know anymore what it's about. But you have to imagine that the matrices that we are dealing with are very, very big. You know, our model that we are using has about 110 million parameters. So you get an idea of how big these matrices can get. What do we need to are what's called nonlinearities in order to really learn all possible functions or to approximate them. And you can see those crazy functions on the left bottom side, like sigmoid or ReLU. They have fancy names like rectified linear unit, which are just throwing away the negatives. But yeah, you need them. And what you also need, the third ingredient, is a function that indicates how far away you are from perfectly predicting the output that you expect from your input, right? And that's called the loss function. And having such a loss function, you can calculate this loss by feeding in some data and comparing the output to the expected value. And then you can do some basic math, like taking the partial derivative regarding all the parameters and having this, you know, in which way you have to tune your parameters. Do you have to lower them or higher them? And by doing this over and over again, not just only for one data point, but for 10,000, 100,000, even millions, you're constantly decreasing your loss and your model gets better and better. And just to give you another hint, if you're also a visual person like me, I want to recommend you neural networks and deeplearning.com, especially chapter 4, because you can actually try and fiddle a bit with neurons there, so you get a better idea how training really works. Okay, so this should be enough to have some basic insights into how neural network training really works. And we are now going into the architecture of our models, because that's another basic question. How do you connect those matrices and nonlinear functions in order to make it easier for your model to learn the respective function? And there is some key idea that you can find in almost any deep learning domain domain. It's using the same information multiple times by applying different transformations. This not only is present in current NLP methods, but also in, for example, the image domain, and also to the idea to incorporate context like locality, or in NLP what we have is attention. This is another point. For example, if you're doing image recognition, because it's such an easy example, you're not just looking at one pixel at once, but you're also looking at the surrounding pixel. That's what we mean by context. And in NLP, with attention, you have a similar mechanism that is quite more complex, but it basically achieves the same goal of incorporating context. Just to give you a brief history of deep learning network architectures, I just want to show you this because we are using BERT, which was developed in 2018. And I don't want to get too much into this, but the key phrase here is that a lot of concepts have been developed in deep learning networks that have been transferred from one domain, say image recognition, over to the NLP part. And I think this is kind of a insight that is that also resembles the key idea that Jonas was talking about, which is transfer learning. So that's pretty interesting, at least for me.
Jump in here again before you go into French. There's another question of Said, and that's a little bit connected to transferring it over from the image domains. Are there ways to visualize the different layers in the context of NLP, like to do it for the images?
Oh yeah, there is. I'm gonna show you a picture in one of the last slides about attention, so you can visualize attention. And this is pretty cool work. And we're gonna look at two pictures that we took from our model.
All right, thank you.
Okay. So now we are going to look where we're coming from with BERT. So what is BERT? And we have to start with basic NLP deep learning. One of the first applications of NLP deep learning was neural machine translation, where the transformers architecture has been developed. And a basic neural machine translation model works like this. This is one of the awesome visualizations from Jay Alamar, by the way. So what you're basically doing, you're feeding in the words or the sentence of one language into a encoder component. The encoder converts it into a context vector, which depicts the meaning of your input, and then you feed it into a decoder component, which produces a sentence in the different language out of it. And what BERT actually is, it's the left-hand side, it's the encoder component, because we are interested in more NLU, natural language understanding. So we want to interpret text, convert it into a vector, so we can calculate with it and solve different tasks like classification, like sentiment analysis, and all the stuff Jonas already mentioned. And now we are going to get a little bit deeper into BERT. And this is also Jay Alamar's work, and on the left you can see the basic structure of BERT, which consists of 12 similar encoder layers. They all share the same architecture, but not the same parameters. On the very bottom, you feed in text. For simplicity, these are complete tokens. Actually, you would feed in sentence piece tokens, so word parts. And for each of these word parts, you get out a context vector, right? That represents the context-sensitive meaning of these words. And on the right side, we have opened up one of these encoder layers, and I don't want you to look at all the details here, but what's important here is to understand that the only part here in this encoder layer that really focuses on incorporating context from multiple tokens, from multiple word pieces, is self-attention. All the other stuff is just within its thread from bottom to top, and self-attention is the only mechanism here that incorporates the context, and that's where we are heading. That's what we are going to dig deep, and we are even showing some code for this. So let's begin with self-attention. And here we are. Here are our beautiful attention visualizations from our model. So to begin with, the semantic meaning of words is context dependent. We saw this in Jonas' examples, like the bat examples. Is it now an animal, or is it a sports equipment? The semantic meaning of this is completely different. However, it's the same representation, right? And the idea is this: we calculate scores that depict the corresponding influence of surrounding words. And then we incorporate the meaning of the surrounding words according to this score. And you can see this on our example visualizations here. We fed in the sentence. Unfortunately, it's German because our model only speaks German. But I hope you get the idea. We fed in the sentence, and you have on the left side the words that you can click on, and if you click on them, you see from which other words they are their meaning is influenced the most. And as you can see, the word "see" is most influenced by Steuerberater in this attention head, which is a pretty cool stuff that the model is capable of doing so. On the right-hand side, you can see the other way around. So if you click on, say, Steuerberater, you can see which of the other tokens incorporate most of their meaning from Steuerberater, and that's here DATEV and Mandanten, which also, at least from our perspective, makes a lot of sense. I just have to tell you this, if you're interested, especially because the question already has arisen. There's this BERTWIZ, which you can use for all your models that are using the Hugging Face Transformer library, so you can easily visualize this stuff. That's pretty cool. And now we're going to look a little bit more into the details, how attention really works under the hood and how it's calculated. Well, basically what we need are 3 transformations or 3 matrices. If you want to transform a vector, we just need a matrix for it. So on the right-hand side, you can see the green matrices are basically input vectors or the raw embeddings of word piece tokens. And in this example, we have 2 of them. So it's basically 2 words here, just to give you an idea what's going on here. And so we have 3 transformations for these embeddings. One of them is the key transformation. It basically asks the question, does the keyword's meaning depend on me? And we also need the query transformation here, which asks a question, does the keyword influence my meaning? So these are basically 2 components from which we are calculating the attention scores. And how do we do that? Well, we get vectors out and we are just taking the dot product. And if you want to do this on scale, if you're feeding more than one word into it, we are just taking the matrix product. And by applying a normalization and the softmax function, we can calculate what we would maybe call probabilities that depict the grade or the amount to which
Can I jump in again?
Yes.
There's a question from Ulrich. If you're there and if you would like to unmute yourself, you can go now.
Hello, if you can hear me.
Yes.
Yes, great. I was just wondering what you meant by the, what exactly you meant by the term word piece token. You used it several times now. Do you mean like word vectors? Because that's what from the visualization I would assume it is meant. Thank you.
Yes, basically what I mean by word piece tokens. Well, word piece is a method to convert your sentences into single tokens, right? And what you would normally do in classic information retrieval, you would just separate them by white spaces or something like this. With word piece, you're doing this in a more clever way. So you're really focusing on word parts, and that's why this method is especially good in the German domain, because you have a lot of compound words, you know. And when we are talking here about matrices, then we are assuming that those word parts, I call them now, which is what I mean by word piece tokens, are already converted into vectors. And how do we do this? If we are looking on one of the earlier slides, there is this initial layer, you could say, before the encoder layers, that is a basic embedding layer that converts all of your input sentence piece tokens into vector representations. Does this make some sense?
Yes, thank you very much. Thanks.
Okay. Okay, so as I said, we expect that these are already numbers, right? These are vectors that represent word piece tokens, and we have in our vocabulary we have 30,000 different word piece tokens of them. Okay, so where are we going? Okay, I think I stopped by explaining how to calculate the attention probability by using the key and the query transformations, applying the matrix product, normalizing, and applying the softmax function. Then we have basically a score that you can view as a probability that says basically how much of all these tokens influence the meaning of, say, this token. And in this case, the value might be, say, 95%, and this might be 5%. So just you get an idea. And the last transformation that we are applying is the value transformation. And this should simply depict the word's raw meaning. So we are just multiplying our self-attention probabilities with our value vectors and adding them up. And then we have an aggregate or a summation of all the context information for our token in question. And that's basically how self-attention works. And to confuse you a little bit more, we are now going to look into code. And how this is really implemented in the transformers library. So what are we having here? This is the basic script that I've used for generating our attention pictures that you saw earlier. And this is the same sentence that we are feeding in. And speaking of sentence piecing, you have a tokenizer, and this tokenizer separates this string into, as we'll see.
Can you zoom in a little bit, so it might be easier for people with smaller screens to also see it?
Excuse me?
Can you zoom in a little bit or make the font bigger? So it might be easier for people with smaller screens to also see it.
At least I'm trying. Yes.
Thank you.
Okay, you're welcome. Okay, as you see, we are here. What we have here is a tokenizer, and the tokenizer's job is to separate the string, the whole sentence, into word piece tokens. And as we'll see in the coming debugging session, there will be 23 of them. And now we are just going in. Oh, wait, this was the wrong button. This is the right. Okay, so now we hit that breakpoint. And we are stepping right into where the magic happens. I just have to zoom out a little bit to show you this. Okay, so where are we? We are in the forward function of the bird self-attention, which is a PyTorch modules, and all PyTorch modules are structured like this. You have a constructor where you define all the stuff you want to do, right? So these are basically, maybe some of you already recognize that there is a query, a key, and a value property here, which are basically our transformation matrices. And these we are using in our forward function, where we step our data through the model. And what we are getting in here, just want to show you what we have here. This is a tensor, so it's a more dimensional array, you could say, and it has the shape 1, 23, 768. So 1 is the batch size, which means how many sentences we have. We have only 1 here. 23 is the sequence length, so we have 23 sentence piece tokens, and 768 is just the dimensionality of our model. So if it converts something into an embedding, it always takes 768 numbers, right? And we are now trying to convert this according to the attention algorithm. And first I have to state another thing. What we were looking on before, we were looking on only one attention head. But as we saw in one of the earlier slides, one of the key ideas is to use the same information over and over again using different transformations. And that's basically what's also happening here, because we are applying this 12 times, right? We have 12 different attention heads. Then there is the attention head size. So this is basically the output size of our matrix. And there's one optimization here. Instead of having 12 times a 768 by 64 matrices, we only have one big matrix. This is common practice to keep it efficient, right? So this all our matrices are pretty big matrices, which are 768 by 768 matrices. And now let's apply them. So we're just applying the query, then we are applying the key and the value matrix. Then we have to transpose them because the input is still has still the shape 123, 768. We have to split them into the 12 attention heads, and that's what we are doing here, because we had those optimizations of the big matrices. That's what we're going to do here. And now we can see that our shape is now 1, then the attention head number 12, then the sequence length, and then the basically embedding size that such an attention head spits out. After which we are seeing the matrix multiplication between query and key. Then we are applying our normalization and the softmax. So now we have our attention probabilities. We can have a brief look into this, and you can see in the maybe the second value is a rather big one of 39%, or the others are a little bit smaller, just so you get an idea of what's going on. Some stuff we don't need to worry about here, dropout, which is only necessary for training. And then we are doing the last matrix multiplication by just multiplying our attention probabilities with our value layers. And as we now have a shape that is focusing on our attention head numbers, so we have still our 12 different matrices here. We have to change the dimensionality or the order, let's say that. So we put the sequence length in the second place and the attention number in the third place. That's what's happening here. And then all we have to do is to squeeze our attention head vectors, which is 12 by 64, into one big vector, which we are expecting as output. And that's what's basically happening here. And now we have basically the same size than our input size. So we are back at 1 sentence, 23 sentence piece tokens, and an embedding size of 768. And that's basically it. That's how attention works in detail in code. And all I can say now is thanks for attending. And I'm looking forward for answering your questions.
Thank you so much to Thomas and Jonas for this very nice presentation. Are there any questions? I, of course, would have one. So at DATEV, what's the vision, or what's your vision for taking this project forward in the coming years?
Yeah, I mean, maybe Thomas, should I start and you elaborate on it, or okay? So first thing we are really looking forward to try out is the evaluation of the training from scratch, because all the results you've seen so far is just adaptation, and the improvements are already very cool. So we are really want to try and evaluate more from scratch. Then, of course, like new use cases, and what would be really cool would be putting the model into production and incorporate it in our products and enhance our search. We have an internal search. Thomas is working on it, and they are introducing neural search there, and really like improving search results would be an amazing thing. We're working on it, and even the tiniest improvements, when you have millions and millions of search requests, then even tiny improvements, and we already have tiny improvements. So that's just amazing. So that would be our vision.
Thank you, Jonas. Thomas.
I'm afraid I have not much to add. That's crazy because we have the same vision. What? No, I think almost nothing to add. We are basically looking into multiple directions now. One of them, as Jonas said, is training from scratch. How can we improve what we've already done? And the cool thing is we could also apply the POC models that we train to real data. That's, say, a small step, but it's also a good one. And now we are trying to do the heavy lifting and on real on use cases that are much more challenging.
Maybe one thing I can add, just a little spoiler. So we're also working on sentiment analysis, of course, and we just evaluated our model, and we compare it to other models or other reported F1 scores on, let's say, German data, which are kind of similar, and we are outperformed. And so at the model, there is at least no better published F1 score than the F1 score we achieved. So and that with adaptation. So let's talk about again when we are doing the training from scratch. So we are still at the beginning, I have to say. So NLP is just.
Thank you so much. It looks like a very interesting vision, and might sound like another talk at a meetup at some point in the coming years.
Yeah, hopefully we can come again after our deep dive.
Cool. And let me read out a few of the comments. So Johannes says, thanks a lot to Thomas and Jonas. No question, but great insights into applied NLP in a big company. Then your colleague Dominic Bayer says, really cool presentation, very nice. Jens Albrecht says, great talk, guys. I really like the deep dive at the end.
Cool.
And then we have Patrick saying, thanks for the talk. And then he would have also a question. Patrick, do you want to join the call and ask a question?
Hi, yes. So thanks for the talk. My question is regarding the search you mentioned, so the neural search. So given it's a live system, did you do any checks regarding runtime already? Because I mean, BERT models also tend to be quite runtime intense in inference part then.
Yes, that's a big problem. If you want to do it on ordinary hardware, on CPU for inference, I'm afraid you can't do that, especially if you have a system that needs to scale to enterprise scale, I would call it. But there are some methods. I mean, one of them is to actually run it on GPUs, which is kind of very expensive. There's also the approach of distilling models, that you're training smaller models on behalf of bigger models. But to be honest, we haven't investigated this to the extent so we can say, that's the solution or that's the way to go.
Okay, thanks.
Thank you, Patrick. On the order of questions, we have Zaid, and afterwards Philip, and then Armin. Zaid first says, thanks for a nice talk. And now would you like to unmute yourself to ask a question? Okay, Mike has a problem. Then let's go to Philip.
Yeah, thank you very much for the talk. I was just wondering if you can recommend any educational resources or courses for PyTorch or deep learning in general. I mean, of course, there's the typical Coursera courses, but maybe you have something in particular that helps to work with real data.
Yeah,
I mean,
maybe
Thomas, go
okay.
first.
Maybe the ones that yeah, I grew up, I would say, that are the Fast AI courses, fast.ai. I don't know if you know them already.
I heard.
They are focusing on people like me who are coming from a coding domain, right? I always liked the top-down approach of them. So you're just in the first place you're viewing code, basically only say 2 lines of code, and then the magic happens, and then you're digging deeper into this, and this is pretty cool, I think. But there's a lot more. What's also pretty cool and completely on YouTube, I think, are the Stanford courses on NLP deep learning. They are very good. I would recommend them. And as Jonas already said, Jay Alamar's blog is amazing, especially if you're thinking as visual as I do. And yeah, I don't know, Jonas, do you have anything else?
I mean, it depends a bit on your knowledge level at the moment. So if you want to have something which is kind of hands-on, I can recommend on Udemy. It's a course I have done it by myself. It's by Jonas Seeberger. You could also shoot me an email, and I can I can send you an email back with some sources I like a lot. And the course of Jonas Seeberger is good to start. I mean, it's not digging deep into all those theoretical aspects. He assumes that you know them already. It's more like a hands-on course, and you work with data. You do some preparation, then data cleaning, and so that's quite handy and quite nice. But there are a lot, and there are also a lot of really good free sources, like the blog of Jay Alamar, Thomas mentioned, the blog of Sebastian Ruder. There are tutorials of Andrew Ngier. So there are a lot of stuff out there. You can shoot me an email, and I can send you one back, no problem.
Great, thank you very much.
And if you can also shoot me the email, then I would just put it, if it's okay for you to share, you can just add it as a comment on the meetup, so the whole community can also look at the resources.
Of course, sure.
Cool. Said wrote me problem solved, Mike. Do you want to try again? Would be your last try.
Yes, thank you so much for the nice presentation.
You're welcome.
Regarding to incorporating the knowledge domain, I have a kind of discussion for that. I mean, for example, in my case, I use such contextualized based language models in order to augment my data, so for data augmentation, basically. And the challenge that I am facing is that I am facing the lack of data, so I don't have that much of sentences to be augmented. The point is that maybe in different domains you have common sentences, and when you say that I will just focus on this domain, you maybe are filtering some sentences and data points. And the other thing is that you may somehow repeat yourself, because you, for example, feed the sentence with a sentence just twice or multiple times. You know what I mean? In the fine-tuning phase, let's say. So how do you see that?
I think that's really yeah. This is. I think we also saw this by applying the back translation stuff that we got out the same output as input went in, and it was kind of difficult for us to get around this. So we tried just both. We just made the data augmentation, and we took a distinct operation on it and trained the model. And the other part was just to leave it as is. So because in the end, if you put some out, then you're also shifting some bias, I would say, towards those who are slightly different, but not very much different, because they are they are over proportionalized in the data set. Actually, I can't tell you what we ended up using as the best model. I'm not sure.
My proposal is to use, for example, information retrieval methods in order to see the intersection of the sentence of the domains, to be honest, and let's keep them, because as you said, one of the requirements of these networks are the data. The larger data set you have, the better performance you may get. I don't know.
I mean, it kind of thanks, Said, for your comment. I think it kind of depends on your domain. So of course, there will be domains which are not so distinctive. So you could use like also knowledge from other domains because they have a large intersection. But I mean, especially in our domain, we got so much data actually, just when we use our domain data. So I would say there is no real right or wrong. So if there is a lot of intersection, I mean, it's a very interesting point, to be honest. So if there's a lot of intersection between domains, keep them. If not, yeah, I mean, we are in a luxurious position that we have enough own domain data. So DATEV domain data. There's a lot of like the German legal corpus. There is this text corpus. So we have a lot of domain data publicly available and own domain data.
Thank you so much.
You're welcome, Sid. Thanks.
Right. For the order of questions, we have Armin, Christian, and Michael. So would Armin, you want to go next?
I actually didn't have a question, just had a comment that if runtime is an issue, I recommend to check out either pruning methods or performers or linformers. So there's even lambda layer. So it's actually also a lot of research came out last year or last 2 years maybe already that actually deal with this issue of inference or performance in general, also for training.
Yeah, you can always do that. Thanks, Armin. Yeah.
Thank you. Thanks. Christian, you want to go next?
Yes, sure. Thank you. Good evening, and thank you for this big presentation to the new topic for me. My question is about the mentioned pains by transferring or the portability between Linux and Windows environment. Is not based on Java virtual machine, or which is the background of the difficulties?
We are completely in Python here. So did I get it right? You're talking about Java virtual machines. I just didn't get it.
No, I mean, yeah, to transfer the models, the developer models in between Linux and Windows, it's I think it's about another topic and not Java virtual machine. Yeah, which difficulties there are inside this field?
Well, basically, it shouldn't be too much difficult to just shift the models around. But what's really the pain is to make the environment work, because you have different packages, different architectural packages for Linux and for Windows. And this was especially when we had the Apex extension, which you actually had to compile against your CUDA compilers with the right PyTorch version and the right CUDA toolkit version. This was basically most of the pain. Now that Apex or automatic mixed precision is included into PyTorch, this should be a lot easier, but it's still not that easy to really get the same environment. If you really want to compare results.
I mean, maybe I can add something. So Christian, thanks for your question. It's actually not an NLP problem per se. It's more like this old Windows versus Linux problem in the environments, as Thomas pointed out, and actually transferring the model, there's actually not much problem. So, or there's actually no problem, but the real pain, as Thomas pointed out, is like setting up environments and problems with the CUDA driver. So it's not an NLP problem per se. It's an old game, Linux versus Windows, actually.
Yeah, and to build the frameworks, the environments.
Yes.
Yeah, understood. Thank you very much.
You're welcome. Thanks for feedback, Christian.
Thank you. Michael first says thank you for the presentation, and then you also have a question. You want to ask it.
Yeah. So thanks for sharing your program and all the slides. And after the theoretical part, you also showed some of the program code. Is a part of that available somewhere on a public repository?
Basically, what I showed wasn't that much. What was really my code. I try to always reuse as much as is possible, and you can check out all the stack stuff and links that I put on the slide of the software stack, where you can find all the libraries like transformers, like farm, and Birdwiz, which is kind of a it's not a PyPy or Conda library, so I think it's really just on GitHub. I can share this.
It's just on GitHub. Yeah.
Yeah.
Maybe we can put that into the comments with
Sure.
yeah. So maybe it's interesting for everybody. I mean, we couldn't maybe to fully answer your question, we couldn't really put our own code on GitHub. That's not possible. The company wouldn't allow that because due to restrictions. Let me put it like that.
Yes. So, I was not talking about your internal text data, just the general one, so you can see how others do the learning.
Yeah.
Okay. Thank you.
That's all open source. You can find it on the internet.
Thank you. And Thomas just posted the link also in the chat to the GitHub repository. Are there more questions? So last call for more questions. But if there are not more questions, then thank you very much again to Jonas and Thomas for this very nice presentation. And also to the audience for the very interesting questions and the discussion. And with that, I wish everyone a great evening, great rest of November, and then see you on the next meetup on the 1st of December with a talk from Google.
Thank you very much, Alex, for having us. It was quite fun. Thanks to everybody.
Thank you.
Thanks for having us.
So Diana also says thank you very much. And then we have another thank you both for the great explanations. Another thank you from Ulrich. And with that, again, everyone stay healthy. Have a great evening. An excellent rest of
Goodbye. Ciao.
November. Bye-bye.